Good afternoon. I'm Robbe. I'm part of the hardware team here at Comma, and today we're going to talk about how the device is built. So, first of all, I think a lot of people, when they think of Comma, they think of an AI company. Like, we do a lot of research. A lot of our people are working on software, on machine learning. But fundamentally, Comma is also a consumer electronics company. Like, I mean, we launched a new product. This is what funds our development. So this is a pretty important part of what we do. It's also not like we're selling like simple electronics. Like, we're selling electronics that's somewhat comparable to like a modern smartphone. Like, if you think about it, we have a high quality screen. We have high quality cameras. We have a bunch of compute to run the machine learning models. We have connectivity. We have network connectivity. We have LTE. We have Wi-Fi. So yeah, it's not a simple product to build. So we started out a few years ago with the Elon. Elon was a pretty simple product to build. I mean, we basically we didn't really care about all the advanced features. We bought a smartphone, like all the advanced features already in a box. We slapped a heatsink on it to manage the thermals. Put it in a 3D printed case. Yeah, it's easy to produce. It's simple. It works, but I mean, it's not really a consumer electronics product, right? After that, I think it's about 4 years ago now, we launched the Comma 2. This is basically a refinement of the Elon product. So that the most advanced features like compute, sensors are still inside the metal box, so we didn't have to care about that. But we integrated the electronics that talk to the car into the case. We refactored the way that we connect to the car so we can support more cars. And things got a little bit more complex. Like, we started to have to build more procedures in-house to like make sure that the changes we made were tested well, that the production processes were good. But then, 2 years ago, we launched the Comma 3. It was a pretty big step. George always talks about the fact that the Comma 3 is the hardest product that we'll ever have to build. And I do believe that that's true for a few reasons. For one, like all the sensors, all the display, the compute, the electronics, they're all custom built in-house. They're designed in-house. This is something that we'd never really done before on this scale. So it took a lot of engineering effort, a lot of time improving all the processes to get this to build. Not only to design all the individual customized components, but also to integrate them nicely into one like little box that looks nice, that functions well, that is a form factor that people actually want to use. So that's what we did back then. Then this year, like, we've obviously launched the 3X that George talked extensively about already, which is just a refinement of the 3 with kind of D added. So we're already on the downslope in terms of complexity. So in the future, I think we can go even a step further. Once we get to larger numbers of devices sold, we can actually start talking to manufacturers to also get the modules that we still use to do connectivity. Like, we still use the Crackdown module for LTE. We still use a system module, as we refer to it, a SOM, for the compute. But we can start integrating that all into a nice device, and then we end up back to something that looks more like a smartphone. Again, like, if we get to those numbers, we actually can customize these individual components more so that the integration will also be easier. So I think it'll only get easier from here. So how do we do it now? So there's actually quite a lot involved in the whole process. So to give you a sense of that, I've made up this little nice design of like the basic life cycle of a product within Comma. I don't think it's too dissimilar to other hardware companies, but it's good to go over it anyways. So we start with a concept. So we basically think about like what the form factor will look like, what features we want to have. Once we've got that nailed down, then we go over to a design step where we design all the electronics, all the custom parts, the mechanical parts, the case. Then we get prototypes built. Then we get them tested. If they're not good, then we go back to step number 2. Usually we iterate like 6-7 times before we get a prototype that's ready for manufacturing. Then we actually can put it into production, and after that we can ship it out to customers. Now, if it would stop there, that would be nice, but we live in the real world, so we'll also get warranty returns. For the 3X, compared to the 3, getting the concept down was a lot easier. We basically have the exact same features except for the addition of CanFD. We still have the same kind of form factor. A lot of the components stayed in relatively the same position, so that part wasn't actually too hard. I actually found a picture of the whiteboard where we sat down and wrote down all the changes we wanted to make. And you notice there's a lot of times we mention the word no in the feature list. So we removed the PCIe lanes because we don't have the NVMe drive anymore. Removed the 3.3 power rail, so that made the power architecture easier. We removed the external siren. Like we used the speakers we already had in the device to do the siren part. We removed the USB hub because the Panda now talks over SPI to the main device. So we removed a lot of stuff. And as Elon always says, no part is the best part. So that's the general goal here. So once we know what we're building, then we get to the design phase. So the biggest part of the design, I would say, is the electronics part, so the main board, which starts out as the schematic on the left. So that's basically where we do we select all the parts that will make up the whole design. We get them to work all together. Like we think of all the edge cases the device might be in. Like when you shut it down after a while, like the power draw needs to be low. Like that kind of stuff all gets integrated and thought of when we do the schematic design. After we're happy that and we think that we made all the changes that we needed to make in the schematic, then we move over to the board layout. This is actually a picture of the PCB layout of the Gamma 3. As you can see, it's relatively complex. So this is the part where we place all the components down in a sensible location to make it fit in the form factor. We design the outline of the board, and then we connect all the components together with traces on like 6 copper layers to get all the requirements that we want. This is actually a pretty manual step still, because there haven't been very good software packages out there that can do this automatically, even though you might think that it's not that hard. Like you just connect stuff up together that needs to be connected up. But turns out there's a lot of design requirements that you need to think about. For example, all the high-speed traces that carry a lot of the data from like the cameras to the compute, they need to be impedance matched. They need to be on layers and far enough apart from other stuff that they don't have crosstalk with different lanes. You want them to not have any electromagnetic interference. You don't want to emit any RF noise that you're not allowed to, because that might also degrade GPS or other devices in the neighborhood. But it's actually quite complex. So this process, like if you start from scratch, it probably takes 1.5 to 2 months to get it down. And then future revisions are obviously easier because most of the stuff stays the same. So let's talk a little bit more about the part selection, because in the recent years that has proved to become more difficult because of all the shortages going on. And not only that, but there's also the thing where there are multiple parts on the market with a similar functionality. So getting an optimal design where you can actually mix and match parts to get the same features, it's pretty important. So how do we internally keep track of all like the substitutes that work together, of all the inventory that we have for production, like what components other designs use so we can reuse the same components? Well, we don't always need to reinvent the wheel. So we actually found this software called partbox. It's made by a Polish company. There's just one guy who writes this in his spare time. It's actually really cool. It introduced us to the concept of a customer part number, or CPN. I sometimes also think of it as a comma part number. But, so this is basically a part number that's not like an actual physical part. So that basically just specifies the requirements that we want for that part to be. So we just say, okay, we want like 100 kilo ohm resistor. That's the one I showed now. In an 0402 package, that's like a relatively standard component. And there's dozens of manufacturers that can make parts that fits these specifications. So that's the parts you see on the bottom. So that's the parts that we can actually buy and that we approve to be like a suitable part for the CPN. And we can then order them to make sure that we have enough for production runs. The other cool thing that partbox has is API access. So we also do a lot of CI on our hardware designs, so we can automatically pull from our inventory numbers and that kind of stuff, and I'll go into depth a little bit more in the next slides. So this is a commit that I made to the hardware repo in the last month. Finishes rounding of one of the camera boards, nothing too interesting, but this shows us like all the steps that are run automatically every time we make a change. So the first thing we have is it checks the CPNs. So it goes over the design that you just pushed and it makes sure that every part in the design actually has a CPN like allocated to it. So we don't push designs where we don't specify like what a part actually is, because that makes it harder for production. Like you have to go back and forth and like asking, oh, which part it is. So that's automatically checked that that's all filled out. Then the next step is one we added because on one of our earlier prototypes we made the mistake of putting a capacitor with a lower voltage rating on a power supply line that was slightly higher voltage. So like in a few weeks we would see failures with this. So now we actually have a check that goes over every capacitor in all of our designs and checks that the ratings are actually good enough for the use case we use it for. The third step is a fiducials check. For people who don't know what a fiducial is, so that it looks like this. It's a little dot that you put on a PCB. It doesn't have any function in the end product, but it's very useful in production because that tells the machine like where the board is actually located in the machine, so it can more accurately calculate where it needs to place the components. We tended to make the mistake sometimes where we would order boards without placing fiducials on them, and then we would get them into the manufacturing line. It would be a huge hassle to get prototypes out of them. So now add an extra check. So every time we have a design, it at least has 3 fiducials on every board. Next one, generate GenCat files. So that's a file format that the machines use, so we don't have to manually make that every time we make a new revision. Then we also generate board diff images. So for every commit, it tells you where the copper was added, where it was removed, so we can easily like go back and see which commit actually changed which, what part of the design. Because, I mean, the files look like XML code, so you can't really see what's going on with the actual design on GitHub. So this is a pretty nice sanity check to make sure that you actually committed what you wanted to commit. Then we have generating schematic PDFs, because not everybody has the CAD package installed on their machine, so we just generate PDFs from all the designs, so we can just pull the latest schematic as a reference anytime. We back up some stuff, that's an automated thing. And then recently we've also added the new parts bot. So every time we now push a revision to a design, it checks and it accesses the parts box API I just talked about, and it checks that all the components we have on the design are actually in stock, like locally. And if they aren't, then we just generate a message on Slack saying, hey, please buy these components when the PCBs arrive, and we actually have all the components to build them. Except for the electrical designs, we also have the mechanical designs, obviously. So we do the injection molded case. We do also all sorts of like holders for GPS antennas, for the decams, the mounting plates you see on the right. I don't go into too much detail there because that's not usually what I do. That's Igor in the back there. But we generate these machine drawings that we can send off to the manufacturers. We do some simulation tests to make sure that all the things stay within the limits that we want them to be, etc. Cool. So we're done with the design. We get bare prototype PCBs. This one's blue. You've noticed in George's talk that the PCB was black. That's one of the ways we make it easy internally to track like which thing is a prototype, which one is a production device. Also, we tend to change the color of the PCB every revision we do. So if you have like 3-4 revisions on your desk, like you can easily check like, okay, this is a Rev B, this is Rev C. It's been quite helpful. So now we have blank PCBs. Obviously, they need components. So what do we do now? Well, some people have already talked about our internal production line that we set up a few months ago. So that's the part that will actually put the parts onto the PCB. The main advantages we've seen from bringing this production in-house, because people ask us, like, why do you bring it in-house? You can just pay somebody else to do it and don't have to care about any of this stuff. Well, it's two things. So first of all, it drastically reduces the cycle time. So with our old manufacturer, it would take like between 6 and 8 weeks to get a new revision. And you'd only get like 2 boards, and it's the whole back and forth. And second of all, it's way easier to fix issues. Like for example, we get a board made on our line, somebody placed a component like 90 degrees rotated, we just literally walk downstairs, change the value in the machine, you walk back up, and an hour later you have a new revision on your desk with the required fixes. With the old company, it would be an email chain of 3 days, and then we might get it right. Okay, first machine. So the board goes into the machine, and that machine applies the solder paste. So to stick components down to your board, you need some solder paste that melts in the oven to create the solder bonds. Most mass manufacturing manufacturers, they use a stencil-based machine. So you get these stainless steel-based stencils with holes cut in them, and you have a big squeegee that just squeegees down your solder paste. It's very nice, it's very fast, so it only takes like a second or two to paste the PCB. The problem is it's very hard to iterate with. Like if you make a new change, you have to make a new stencil, you have to reload the stencil in the PCB every time you change the designs out. So that adds a bunch of time with switching designs and making new revisions. This one just has a tube with some solder paste in it, and it just dispenses tiny little dots on the pads, and it's just CNC controlled, so we can just put any design in it, and it works. It's also, the cycle time is not very important in this step, because the whole production line is pipelined. So even as long as this takes less time than it takes to populate the board, this won't hold down the total production rate that we can achieve. So there's actually not that many downsides to doing it this way. Next machine, pick and place machine. So the pick and place machine is loaded up with a bunch of reels of components, and it does exactly what the name suggests it does. It has nozzles, picks them up from the reels, places them down on the board. Our machine also has an extra cool feature that I really like. It does electrical testing as well of every component, of every passive component. So for example, if it picks up a 100K resistor, usually these parts have tolerances because we live in the real world. It'll place them down on the test board, it'll measure the exact value, log it to a database somewhere, like related to the serial number of a board that's in there, so we can, in the future, always look back and see exactly which value resistor was placed in there. It's pretty cool. Next up in the line, the oven. Pretty straightforward. So you just put the board in, moves over a conveyor, it gets hot, solder melts. That's pretty much it. You'd think. But then there's a lot of tweaking in the oven. So the oven has about 8 zones. They can all be set at a different temperature. And then the conveyor belt speed can also be modified. And it's a balancing act between like multiple parameters that you need to tune. For example, in the first 5 zones on this, this slide, you'll see that the temperature slowly moves up. And that's to give the flux contents that's inside the solder paste some time to clean off the oxidation of the pads, which makes it way more likely to get a good solder bond. Then it moves into zone 6 and 7, where the temperature rises up quickly to above the melting point of the solder balls that are in the solder paste. The bond gets formed, and then there's a controlled cool down in the next 2 or 3 zones to make sure that everything settles down nicely. A lot of the components that we use actually have limitations on, for example, the temperature rate, the temperature gradient that they can sustain. So, for example, the image sensors, I think you have to heat up less than 3 Celsius a second and cool down less than 6 Celsius a second. And that's also something that you have to keep in mind when tweaking all these solder zones. Next up in the line, we technically have a functioning board if everything went well. The problem is we don't know if everything went well. Like what if somebody like bumped the PCB, some components moved, or we loaded the wrong part into the machine, or it failed to pick up a part and didn't notice. Well, that's why we have automated optical inspection. So it's that machine. It's basically a fancy camera with a bunch of lights that can move. Just flies over the board and checks out every component and makes sure that it matches a reference picture from a known good board. So this is especially useful in production, where if you're running like thousands of boards, you know that every board actually has all the components and it doesn't have any failures that would be easy to detect this way. There's another benefit of having the machines in-house is that we can do a lot of vertical integration with them. So we talked about partbox having an API. Well, the machines also have an API. So this is some software we wrote in-house to program the machines. Because if you're a contract manufacturer, you usually get like an Excel sheet of all like the parts and the mounts positions that the parts need to be placed at. Then somebody has to like sit there and manually enter like the hundreds of components that are on the design. Select from which CPN, like which MPN is actually in stock, which one's on the machine, which one is not. Well, I mean, we've built a software. It queries partbox, so to check which components we actually have in inventory. It checks which parts are actually already loaded on the machine. So if you have multiple accepted MPNs for a CPN, it can like prioritize the ones that are already loaded. And then we just throw in like the CAD file that we have. Automatically generates all of this. It's literally a 5-minute process, and we have programmed all the machines. So we have built prototype devices. Does everything work? Well, to verify that everything works, you need test plans. So we have very extensive unit tests for every single feature that we want out of the device. So this functionally tests that everything works that's on the board, like you expected it to work based on the design. It also checks for extreme environments. So we do a lot of tests in like thermal chambers to make sure that it goes up to that everything still works at a temperature that it might reach up in a car. It goes down to a certain temperature. It also does some minor stress testing where we like inject voltage transients into certain lines to make sure that the protection circuits we've built in work. We make sure that if you plug in a wrong cable into the wrong hole, nothing breaks. Like all that stuff is validated before we move on. Then if we think that's all good, then we have some more compliance tests. So those are actually mandatory if you want to sell consumer electronics. You have to bring it to like a certified test lab and then make sure that you're not intentionally radiating any RF noise on frequencies that you're not allowed to radiate on. And then there's the second part of the tests, which makes sure that the modules you've integrated that actually want to transmit don't transmit at a power level that's too high, or that they don't create any intermodular effects. And then there's a third step. We do field testing. So we first put them in all our cars. So we have 12 cars in our fleet. It covers most of the platforms we support, but then there's some other ones that the community only has. So that's why we do the EPHOT program. So we have some few members here, I think. You guys here? Yes. And that's actually proven to be very successful. So in this round of EPHOT testing for the 3X, we've actually found 2 bugs. One of the bugs was a software bug with the new panda that's integrated on the board. It was used in slightly different ways than the red panda was in the past, so we fixed some bug related to CanFD. But there's also a hardware bug that was discovered that we didn't discover with all the test plans we've previously done, which was with Jason's third-party long cables. VW users do all this weird stuff with their cars, I don't know. So yeah, we always use the official cables because they're laying around in the office. So it's good to get some coverage from the community as well. So once that's done and we're happy with it, it moves on to production. So we now buy all the parts in bulk. We select the cheapest components. We make sure we have everything in stock. And then we get the PCBs built in black, like mentioned before. We apply the QR code stickers. Actually, a data matrix, not a QR code. But same thing. So this adds a unique serial number to each board, such that we can later on, if it comes back with a hardware failure, we can double check that the oven was set at the right temperature when it was run, that all the electrical components measured their respective values. We can check the AOI images, like to see if that missed anything that it shouldn't have. So that's a pretty nice addition. Then, when it runs through the whole circuit spoke line, the exact same as the prototypes. So then we have assembled boards, and then we move on to all our provisioning steps. So first of all, we have initial provisioning. So this is a step we've added for the 3X. and it basically takes the bare boards that came straight off the line. We just put on the lens holders, the lenses in them, puts them in this nice jig, and it does a bunch of like very preliminary tests. So it checks that all the voltage rails are in tolerance. It checks that we can talk to most of the components. It does like an initial flashing round of the internal panda. And then it has the focusing step. So it's very important that the lenses that we place on the devices are like perfectly in focus, because it's fixed focus, so we can't change it in the future. And it would be a hardware return if they're not. So we made this UI thingy where you just turn the lenses, you try to get the green line to go as high as possible, and then we know that the devices are in focus. Now, obviously, on the bare boards, we haven't placed the SOM or the compute module on the board yet, so we needed to design something else for that. So we designed what we call a fake SOM, which is basically a separate module in the same form factor as a SOM, but that can be powered externally, so we can just keep it alive when switching between boards. This makes sure that we don't have to like reboot Linux every time before we run tests, so that increases cycle times. Plus it has like the voltage testing stuff built in and all that nice stuff. Then the next step is we build them out into full devices. So the heat sinks get placed on, the DCAM gets placed on, the GPS gets placed on, that they get put into the cases, the screen gets placed on. That's quite a lot of steps. In the case, we also add an NFC tag, and you'll see where that's useful for later. After they've been built into their final form, they move on to what we call final provisioning. This is a wooden rack we have set up in our production environment with some mounts. So they get connected up there, and then we run through like a full suite of hardware tests. So we make sure that every piece of hardware that's on the device, like the IMUs, the GPS, the Wi-Fi, the screen, all that stuff, that's all tested. So we make sure that we know that everything works before we ship it out to customers. This is also a place where, like, from time to time, new tests get added because we've seen failures from the field. For example, a few weeks ago, we had some returns of display panels where, like, the touch wouldn't work in like a certain area of the screen. So we just added a test where we just like wipe the whole screen, so we make sure that the whole screen works. And so that's like the procedure we follow to reduce failures more and more as time goes on. After that, we move on to the stress test. So that's another bigger wooden rack. This is only a small portion of it, where the devices are placed on for a 24-hour cycle test. So on this test, we put them under high synthetic loads. So we just max out the CPU usage, max out GPU usage, DSP usage. We run the cameras at full speed, run the fans at full speed, just to make sure that the devices actually stay working for like a reasonable amount of time, because sometimes like stuff works, but then like it heats up and then it stops working. So that's the kind of failures we try to catch here. This is also the place where we do some longer running tests. Like we make sure that the GPS signal doesn't drop for 24 hours. We make sure that if we toggle the fan on and off once in a while, that it starts back up. We make sure that the camera doesn't drop any frames during the whole 24 hours. And those things have really reduced the amount of failures that we see in the field. After they've gone through that, they're ready to ship, so they move over to fulfillment, where we automatically test using the NFC tag, because we know where the device has been. So we put the device on there, on our reader, and then we know if the device passed all of our tests, because that didn't always used to be the case in the old Comma 2 days. In the old office, like, device would get misplaced, or like not all the tests would have been run, and then it would get shipped out anyways. So now we explicitly confirm this. For the Comma 3s, we had to make sure that they were the correct type. Like, if you buy a 1 terabyte one, you get a 32 gig one. People will complain. The other way around, not so much, but still not great. Domestic orders, we include a SIM card for the Comma Prime trials. International orders don't, so that's also something that's verified. This also tells you which harness the customer bought, so we place the right one in the box. It also checks that we have the latest software flashed onto the device, because if it's been sitting in storage for a while, like if we have some excess inventory, it might be on an old OpenPilot version, and the first clone would take a lot longer. So this is something we try to prevent. And then there's the final cosmetic inspection before the box gets shut. There's also an AOI. It's not automated optical inspection. We call it ADA optical inspection because she's the one that does the fulfillment. So yeah. And then the hardware failures. We used to get emails all the time that said, oh, my device doesn't work anymore. And I mean, there's not much you can do about that except for ask the customer to return the device. And then in most cases, it turned out that the device was fine, but it was installed wrong. Or the software didn't support that car yet. Or there was some other software bug that we didn't know about yet. So we recently changed that process and made sure that when there's hardware complaints, people actually provide us with a route where the issue occurs, so that an engineer first looks into the alleged failures, and if there's actually some anomaly going on, then we get it sent back. Otherwise, we tell the customer like what's going wrong, and we don't have to do any unnecessary shipments. This has actually reduced our inbound for influx, like the inbound for the failures, by close to an order of magnitude. So that's been quite good for us. But then the devices that do come back, we have to take them quite seriously, because usually there's something we can do about it. For example, one of the earlier failures of the Comma 3 had to do with the SOM stoppers failing. And it turns out that we used to use a thermal pad on top of the main CPU. And with manufacturing tolerances and thermal cycling, that would put too much pressure on top of the die, which caused some solder failures. So then we changed the procedure to go with a putty-based thermal compound, which reduced the total pressure on top of the chip by 2x. And that practically resolved the issue overnight. Another thing we can do is add additional testing, like for example the touch issue I talked about before. Like we just add another test so we make sure these devices don't get shipped out in the first place. Or we actually can also improve the design, like if it's like an actual design bug. We had one a while back with the red pandas, for example, where we didn't account for people plugging in a USB cable with 12 volts on it on a port that wasn't supposed to get 12 volts, and then it would blow out the CAN transceivers. So that's just fixed. We made a new revision. Doesn't happen anymore. And that really translates in the failure rate. So George already alluded to this, but the all-time failure rate of the Comma 3 has been at 9.2% now. It's an interesting number, but it's actually more interesting to look at what failure rate's been over the last year. So we lowered it to 3.9% already, just by improving all these processes. To put that into a little bit of perspective, George already did some of this, but iPhone 6s, 22%, recent iPhones, 3-4%, Xboxes, 22%, PlayStation 3s, was it 10%? We're actually close to a Wii. That's pretty good hardware, apparently. But we intend to do a lot better with the 3X. I think with some more improvements and with a more reliable design, I think we can probably get it down to like 1 or 2%. So that's pretty good. So I mean, George gets to announce hardware products. Why don't we also get to announce something?
Wheels.
That's not on there. You guys know harness boxes? A lot smaller now. I mean, they're in the final stages of testing, so they'll come out in a few months probably. Injection molded case. It will be a lot easier to fit under the covers in most cars. And another one that we're coming out with soon, the new Panda Jungle. So it's a CAN FD variant. It adds SD card support. It adds per channel eFuses, per channel SBU line control, all that stuff that has been very nice for developers, internal and hopefully external as well. So okay, I've been talking for 35 minutes now. I only have 45 minutes, so there's still a lot more that we haven't talked about. There's part shortages, there's torque control screwdrivers, there's packaging, there's injection molding, BOM optimization, cable testing, suppliers. harness production, mounting plates, trough-hole soldering, display calibration, laser depanelization, pandas, comma bodies, you name it. The hardware team has a lot to do. So if you're interested, reach out to us. We can definitely use an extra hand. Or if you have more questions, then feel free to ask him now.
All right, thank you, Robbe. We got a question up here in the front.
Thank you. You talked about compliance testing. Are you planning to do only FCC, or are you looking also European one like EC and others?
We've done the FCC one now. The European one's very similar, so we'll probably be compliant with that as well.
Great.
So the harness connector is changing because you've got a smaller box there.
Yes.
So how do you make that? What's that equation like for making the trade-off? Is it time to?
Yes. So I think the old one was a 24-pin, if I'm not mistaken. The new one is a little bit smaller. I mean, we had to because otherwise the case wouldn't be smaller. The new connectors will just come with the new harnesses, so we'll have to move over that production a little bit. But functionally, there's not that big of a difference. It doesn't have a mechanical relay anymore, by the way, so we'll get rid of the little click you hear when Open Pilot starts, but it'll be a lot more reliable, hopefully. So that'll be good.
We got any other questions? Oh, in the back, I'm coming.
Hi. So I was impressed by your automated testing on commits to the repo. How is it that you do the diff between the old board and the new boards?
Well, it's not super efficient computationally, but we've gotten Eagle, the cat package we use, to run inside of the CI Docker container. So we basically just spin up Eagle, open the files, generate the Gerbers, then generate PNGs from the Gerbers, and then we just do an image diff on the two images.
Sweet. And we're also looking for hardware engineers. Are there any like networking events that you know of in San Diego where we can all?
I don't really know of that many, actually, no.
The truth is that Robbe is based in Belgium.
That's also true.
So he definitely does not know about the happenings in San Diego. Oh, we got a question back here.
I'm wondering, do you have any interesting stories about weird issues that took a long time to track down and ended up having an interesting cause?
We have so many good bug stories.
We have a lot of them.
There's much bugs, Nabil.
On both the Comet 2 and the Comet 3s, we've had a lot of GPS troubles. Apparently, like the 845s, the main chips, they leak quite a bit of RF across the whole spectrum, so you have to isolate them very well to not affect GPS. On the Comet 2s, we had an issue where the GPS antenna has this internal LNA amplifier. So it amplifies the signal, but then we had an issue where it leaked out after the amplifier into the heatsink, and then got coupled back into the antenna, so then we would get like a feedback loop. That one took a long time to track down. What other ones have we got?
How about last week when a vendor sent a wrong component and mislabeled it?
Oh yeah, that's another great one. So last week we were placing inductors on the boards, on the 3 axes actually. Don't worry, we fixed it. But so we ordered 1 microhenry inductors from a reputable supplier. They came to us, we loaded them into the machine, and then Igor, the hardware guy, he needed one, so he just took one off the line. And when taking it off, we looked at the reel and it was like, hey, there's 2 labels on here. One of them says 1 microhenry, one of them says 2.2. It turns out it was the wrong part. So yeah, got to be careful even with official distributors.
So we heard George talk about custom ASICs. Where does this stand on the hardware roadmap? Have you guys thought about it at all?
I think George has some architectural plans, but I don't think that's going to be concrete anytime soon. Yeah, we're quite far off from the budgets needed to spin out ASICs.
So people frequently express concern over the thermal resiliency of the devices.
Yeah.
Can you speak about the steps that you take during production for both the C3 and now the 3X to mitigate that?
Yes. So, I mean, the basic process we follow is we just test them at extreme temperatures, and then we make sure that the parts don't fail at those temperatures. We just cycle them lots of times, and then we fix the issues that arise. The second part of the thermal issues is also not necessarily for failures, but also for like user experience. For example, when it's like sitting on your windshield, when the sun's blasting on it, the device can get quite hot, and you want it to cool down as fast as possible. So you actually want to reduce the total thermal mass in the device. So yeah, there's quite a lot of consideration going on in that regard. But so far, with like all the improved soldering processes, we don't see that many thermal cycling failures anymore. So.
Hey, I'm curious about the root cause process. So, are you? So your team is manually doing that, the root cause, about different bugs or occurring in hardware, or there's like automation inside all that?
Well, when we get failures back, we often just run them through the provisioning tests again. And that usually gives us that narrows down the component that actually failed, and then we disassemble the devices, look at them under microscopes, and then trace down what the actual issue might be. So it's mostly a manual process, but we use some of the production tests to guide it.
All right. We've got time for a few more questions.
I had a question about the GPS module in the QUTEL. How does that compare to, I think you were using a Neo M8P?
Yes.
What do you think, is it worse, better?
I think performance-wise it's pretty similar. I think we gotten the Crackdown into a mode where it sends us the actual raw measurements and turn off all the processing that it does inside. But the Crackdown module uses Qualcomm chips inside, and phones have pretty good GPS these days, so the hardware level is quite good. So we get about comparable performance with the U-Blocks modules as we do with the Crackdowns now.
Robbe, what's your favorite part of the 3X process?
The favorite part?
Yeah, which one brought you the most joy?
Ooh, that's a difficult one. I really like the new image sensors. Like they're nicer, they're easier to route, they have better specs. Yeah, they're cool components.
We got any additional questions? All right.
How do you manage being in Belgium while they're here? If you're the hardware guy.
Well, you get used to it. It's I used to be in San Diego for a year, so I know the team very well as well. And then we communicate over Slack, so I make sure when the US is awake that I get all my questions answered and I can continue working the next day. Sometimes it's nice as well, like you're sitting by yourself, quiet, and you just plow through it.
Robbe is our only remote employee. That's a testament to how talented he is.
Also, he comes in about once a quarter.
Yeah.
Every Wednesday, Robbe and I have lunch meeting.
Yeah.
And every Monday, we do a team meeting. Comma's super low on meetings.
Yeah.
We have an all hands, and then a team meeting every week, and that's about it.
Yep.
All right. Thank you so much, Robbe.
No problem.